Hello. Welcome to the third session of the series given by Sandip on the group of self-homotopy equivalences. So today he will be continuing his talk and he will talk on algebraic connection, localization, and some open problems related to the same. Okay.
Okay, thank you. And as said, we'll continue our third talk. So today's goal is basically to see some application. So as the abstract and title was given, I just changed that a bit to just focusing on the mainly few one or two application of this group of self-homotopy equivalences, and some open direction that can one pursue, or on which some of the direction that I'm particularly interested in. So let's start. So first, let's see. So it defines certain notion of this group of self-homotopy equivalences, and those were so this let me just write as today's goal. So first is to see some application of this this thing or its variant. So variant, I mean, we consider here a group of this epsilon x is group of self-homotopy equivalences of x, which preserves the base point and consists of the homotopy class of those things. There are variants like ex if these are, instead of fixing the base point, those are homotopy equivalences, class of homotopy equivalences of x that does not no need to fix any base point. So it's definitely a bigger set than epsilon x. So in several places these groups are appear rather than this one. So we'll see one such example of that thing. And also it's very this is one variant is like homotopy. So this is the homotopy class of self equivalences of x. So there is also this x each mu. So these are, so here if x is a H space with multiplication mu, then we consider this set as all again homotopy class of self equivalences of x, which are, so it's just here F stand for free. Okay, so previously this EX was just base point preserving homotopy class. Here it's free homotopy class of self equivalences, and this is again just any free homotopy class of self equivalences of X, which preserves the this H space structure mu of X. Okay, so we are assuming that mu is a map from X cross X to X, such that there is a point E in X, such that mu E comma X, or so just maybe as a map from X to X, or mu dot comma E from X to X. Those are homotopic to the identity map. So this is homotopic to identity map of X. This is also homotopic to identity map of X. So this is important in the when you study H space, some any H space. So there we just don't want any homotopy like any self equivalence, but we also want our that. equivalence to preserve the structure of that multiplication on the space. So on those spaces, these are important class of homotopy of self-homotopy equivalences. So we'll see some of those example application of those things, and lastly we'll see some open problems. Those are like certain up to certain level, some problems were already uh, like done, or some still remains, but for those one needs to develop like some new technique with the known techniques what we have already. Those does not give any other immediate uh, immediate solution to those. So maybe if uh, some new techniques can be developed to solve those problems. So some of them are quite like open for quite long time. So we'll just see some of those, but uh, like those are quite important to like quite important if we can get to like some bit of those things also. Okay, so let's start the first kind of application. Okay, so classification of classification of each vibration over circle S1. So recall that what is a which vibration. So a map P from E to B. This is a which vibration if uh like this map has homotopy lifting property with respect to any space. So what does that mean? So suppose we have any space X and we have this commutative diagram. This sits inside X cross interval 0, 1. So suppose this diagram given to be commutative, then whenever such diagram given, then there is a lift. If there exists this lift, then we'll call this E to B as Hurwitz vibration. So there is also shared vibration. In that case, instead of any space X, we restrict to only CW complexes. So X is any topological space. Okay, so that's called Hurwitz vibration. So classification in general for fiber bundle, if you've seen, so those fiber bundle also have fiber bundle principal G bundle. Those has classification over certain space. So if you recall that for fiber bundle, if we consider like just a analogy, so for principal G bundle over X, so like isomorphism class of those things, those are in one-on correspondence with this X to BG. So this just means any homotopy class of maps from X to BG. So here, if I say for G bundle, so this is also G bundle over X and mod by isomorphism class. So similarly for like this is a famous classification result for any principal G bundle. So let's say principal G bundle and so there exists for any group, there exists this space, this called classifying space of G. So G is a group, then principal G bundle over X that are in one-on correspondence with homotopy class of mass from X to PG. Similarly, for Hurewicz vibration, there is also classification by Stasek uh, that any. So here we don't need any principal thing, but for any, or maybe before just saying that, so I should for in this case, what is this tilde means? Like for principal G bundle, there is a notion of isomorphic bundle. So what is the isomorphism thing for Kurevich vibration? So to Kurevich vibration, let's say I have over the same base space. Uh, so there is for the fiber thing also I need another information. So which vibration this and fiber if and fiber. So which vibration if fiber if this diagram and fiber if first of all this diagram commutes and there is a um, homotopy equivalence from F to P inverse star. So star is some point in the base such that whose inverse image in homotopy equivalent to the fiber F. Okay, so this is the fiber thing. So to vibration. So I'm just removing the Hurewicz vibration. It is understood that I mean to Hurewicz vibration only. So vibrations, let's say Pi from A to B. So the base is remains same and also the fiber. Just the total space are varying. So Pi to B and fiber F are each equivalent. So if there exists map P from E1 to E2, so here I mean I equal to 1. Okay, E1 to F2 and also I need another thing. Okay, so that's also comes with the choice of that thing. Okay, if there is P E1 to E2 and okay, so again the fiber 8 comes with the choice of this G1 G2, so I should input that before fiber 8 is there exists GI map from F to PI inverse star. Okay, so both the 1 2, so the for the fiber thing I'm getting this. Or equivalent if there exists map this thing such that so the diagram is this. So if you have if you want to do here you have a 2 to 2p. This I want to be identity map. This is u1, this is p2, this is p map, and this also I want to be identity map. Okay, this is for g1, this is for g2. Okay, so now I want the first diagram to be directly commutative and other one is this P2 compose P is equal to P1, and so this commute directly and this commute up to homotopy. G2 is homotopic to P compose C1. Okay, so so this is the equivalent condition, and one can check that this is a equivalence relation as well. So we will call this say or denote as denote this as this tilde notation, okay, as E1 homotopic to E2, okay, as bundle, or rather in the thus there are three things. So if E1 P1 E2 P2, okay, B is understood over the same base space, okay, okay, and this is an equivalence relation. So the condition of equivalence is almost same as the fiber bundle or principal G bundle thing. And by H HPF denote the equivalence class of all those bundle, all those vibration over B with fiber F. Vibration with base B. That means E1 to D, where the P maps base and fiber F. Okay. And now the tacit thing says that this HPF, this is in one-on correspondence with the for each such B and F, you will get one space B infinity, such that so this B to B infinity, the homotopy class of this based maps. In this case, this is, so maybe I should just put a star here to differentiate from the original homotopy class of maps from that to this. In this case, this star means just it preserves the base point. Okay. So for there exists this PG. There exists this B infinity. Okay. So this is kind of the B infinity is kind of the classifying space, like a space in this classifying this Purevich vibration. Okay. Okay. Now over the circle, if we consider our base to be circle, then B is this S1. Or in general, even if we just do for any Sn, B to be any Sn, then also on the right hand side, it is just saying the homotopy groups of this classifying space B infinity for this vibration thing. So this on the right hand side, this is very like kind of a very algebraic quantity. But how this is related to the self-homotopy equivalences is that this this homotopy group of this B infinity, this is actually ith homotopy group. It's isomorphic to the I minus one homotopy group of the free, sorry, not T, but the F and the three with one as the base point. Here, take something star as the base point. Okay. One is the identity thing, identity map of it. So we have the fiber. So now this pi I, the ith homotopy group of this B infinity, it's just consider any base point star. Just to that, that is isomorphic to the I minus one homotopy group of this the group of self-homotopy equivalences, the three the, this one, this epsilon x f. So the three homotopy class of self-equivalences of the fiber f. So now using this, if we just apply the condition to for b equal to s1, then it's relate to the case that for b equal to s1, that is this pi 1 of b infinity star is the s1 b infinity, this thing, the same thing as this, and that is isomorphic to the pi 0 of epsilon f1. But this pi 0, this thing of this space, this is being the like discrete space. So this is the same this group, right? So and this is in one correspondence with the this equivalence class of base is now S1 and fiber is F. So knowing the this group, the free homotopy class of self equivalences of its space, let's say F, that is like any element of that thing is giving us a equal like a uh, a class of Hurwitz vibration over S1 with fiber F. So knowing now for the fiber, if now what's the relation between this F and like epsilon F, the free homotopy thing and the based homotopy thing. So note that. So it's a kind of exercise that if the fiber F is simply connected, or like this pi one of F acts on the pi n of F trivially. So we have discussed this thing also before, that if this happen, then this this free homotopy class and the based homotopy class of self equivalences both are isomorphic. So anyway, so for spaces like that, there if we can calculate this group or this group, then we are able to classify all vibration with fiber A over the base space S1. Okay, so that's a nice application of the group of self-homotopy equivalence to in classifying those vibration. So another second thing that I want to say uh, in the application of that these groups, it's me this thing. So so if x is a H space with mu as the multiplication, then um, how like what can we say about these groups or what's the effect of these things in general? So for that we note that this epsilon x or even epsilon x or epsilon y, these as a base homotopy maps only. So they acts as like on the group on the homotopy class of maps. That means if I consider all homotopy class of maps from X to Y, then on those things these sets act. So for let's say alpha belongs to here, beta belongs to here, then I can define a action of alpha on this set, and let's say some, and let's say it belongs to this homotopy class. So it's a map from X to Y and consider the homotopy class of that. Then alpha comma beta, this can act on F as compose alpha inverse. So the action is basically I'm defining as a this as epsilon x cross epsilon y. So this thing acting on the homotopy class. So it's y. So that's a give. That means a map from epsilon x cross epsilon y cross this x comma y, this homotopy class of the set of homotopy class of maps from x to y via this. So it's alpha inverse is in like alpha is an element of ex. So it's the inverse map of that thing. So it's sending so x to x via alpha inverse, and then using f to y, and then using beta it sends y to y. So why alpha inverse? If you put alpha, then it will not satisfy the standard rule of the action. So for that reason, because it's acting on the right, so for that reason, I need to take this alpha inverse. Okay, but alpha is also a choice in that case. Just for the property, sake of property of the group action, we need to take as this alpha inverse. So now this set, epsilon x cross epsilon y, acting on this set. In particular, also similarly, we can say um, just replace this by, let's say, x cross x to x. We consider this homotopy class of maps. So why that we want? Because note that this mu, what we had, that mu is a map from x cross x to x, satisfying that if we restrict that to the special wedge point, so mu if I restrict to x wedge x, then it's just a folding map, right? It's just the notation folding map means it's on the wedge. It's just if x comma e, then it's sending to x, or e comma x, then also it's sending to x. So that is the replacement of the previous writing that mu dot comma e or e comma dot both map are homotopy to identity. So in this case, I should say instead equal that homotopy to the folding map. Okay. So particularly we want to see on these homotopy class of maps how this epsilon x acting. So on this thing, the homotopy class also acts such like as follows. So we can, let's say alpha belongs here and some, let's say p belongs here. Then the action says alpha dot p is alpha compose p compose alpha inverse compose alpha inverse. Okay. So instead of now, like just as the previous thing, but now on x, instead of x, as we have x cross x on that thing, I need to act by two element of alpha. So it's just like ex cross ex thing. So on the right, that thing is ex cross ex, and on the other thing is still just ex. So it's acts like this. So this is again defines an left action of the this group epsilon x on this set. And uh, if we just denote mx by all those multiplications, so mx are just I need homotopy equivalences. Just a minute. No, I don't know. It's just collection of all. So just all those mu from x cross x to x such that mu restricted to x wedge x is homotopic to the Holden map. Okay, so it's just the collection of all possible H-based map on X. Okay, so homotopy class of that. Maybe homotopy, homotopy class of mu. What's that? So this is clearly a subset of this x cross x comma x. Similarly, also one can consider this mu 0x, which is just another subset of this mu x. So let me write as mu belongs to mx such that mu is homotopy associated. So again, like it will from x cross x cross x to x, there are two possible way of using the mu. Either I can take compose 1 cross mu or mu compose mu cross 1. Those two map are homotopy. That's the homotopy associative in that case. So this is a clearly again a subset of x cross x. Like previous one was itself subset, so this is also a subset of this thing. Now on this set also the above uh, ex still acts on this mx as well as m0x. And if we consider this mx quotiented out by this epsilon, the action of this epsilon x, um, so that's actually denoted by m tilde x and the other thing m0x. If you quotient out by the action of this epsilon x, that gives us m0. So this is the definition of it, not tilde. Then Kurzweil actually showed that if x is finite homotopy associative space. So finite means finite as a CW complex, okay? H space or H complex, maybe just to say that it's finite not as a state, okay? Finite as a CW complex. Then the number of homotopy associative multiplication on X, this is always finite. And also prove that this mx is m tilde x is infinite if and only if for some in Betti number of x mass x and solitary number of these times the rank of pi in x is non-zero. If such happens, so these are so this characterizes the number of possible homotopy associative, like not characterized, but at least say when it is finite or infinite for a space, um, like whether the number of homotopy associative multiplication is finite or infinite, or in this case, it's saying when it's infinite. In the first case, it's saying that it's always finite. It's for specific this type of for finite CW complex admitting this homotopy associative H space complex structure. And this also um, relates to the thing that the if you consider uh, this set. This is kind of determining how many, this set is kind of determining how many different multiplication we could have on the space X. Those homotopy equivalences, how they are acting on the, like keeping the structure of the space X with that same multiplication. How many of them are there? Okay. So this is another application, and also there are few others applications. So uh, I'll just keep those things. I'll write some of those in the notes, and you can find them. Just as like it's actually determines the. Uh, we already have seen in the last class how the cosmic of decomposition helps us to conclude about the in the computation of those self-homotopy equivalence group. So those also helps in the other way that for the cosmic of decomposition there is cosmic of invariance, and the post-Mikam invariant, how they're so I'll just write as post-Mikam invariance uh, determination. So for a given Postnikov decomposition, we get Postnikov invariants, and how those invariants changes um, can be seen by the this group of self-homotopy equivalences. Once I see that, also there are application wants this Postnikov invariance determination. So indirectly, those also helps in determining means like extension or lifting problem. And also there is also homotopy action of a group on space also determines. So in the same sense, whatever we have a group action on space, let's say group acts on space, that actually determines a map from group homomorphism from G to homeo of X. So homomorphism of X. So on this set, this is group under composition. So on this homeo X, so these are kind of contained in our E of X, right? Or maybe 3, 1. So some of those actions also this homeo F, like this set sometimes deforms to this homeo X, and then a homotopy action of those groups are actually kind of given by uh, given by homomorphism from these sets. So again, knowing this epsilon x if those again helps us saying the homotopy action of groups on space X. Okay, so these are a few other applications that one can see. So now let's move to some direction of open direction. So first one, that one, the one I'm particularly interested in, that the finite or finite generation of this group, generation of X. Okay, so already in the last class also told there is this Sullivan-Wilkerson theorem that says for a specific uh, X which has finite, if there are that is finite CW complex having only finitely non-zero homotopy groups, for those spaces he says that always this EX group is finitely presented. So still we can like only all the whatever finite generation results are there for general space are for X which is finite CW complex. But in general, for any other space, what we can say in terms of the finite generation of those things. So even for like not even for not all finite CW complexes, still we have the result that it is finitely generated or finitely presented or those things. So so basically to that particularly one particular X that like for I'm interested is take X to be some loop space of some D. So this in general in most of the cases this is a infinite CW complex, but this has a space structure and quite nice space, and in many places this appear as a fiber. For example, path space or free loop space vibration, this appears as a fiber. Now, knowing the self-homotopy equivalences of these groups are quite relatable to saying the homotopy type of the loop space vibration, free loop space vibration, or path space vibration. So path space vibration is quite that's contractible, so nothing much information we need there. But knowing the homotopy, like self-homotopy equivalences of these loop spaces helps us in characterizing the whether the free loop space vibration is trivial or we if we restrict that to specific component of some specific component, how they look like when they are different. So many various those kind of question can be handled once we have some computation tool or on the if we have some finite generation or finitely presented notions for these kind of spaces. So basically the question is determined on the finite generation. So it is whether it's generated by finitely many elements or not. So finite generation or finitely presentedness. Of this E of omega b. Like if we should have some condition on b at least or anything for which this is finitely generated or not. Or related one is that for which like finitely generated there are like if we have two generated there are infinitely many uh, uh, finitely generated groups, but like with two generator itself. But finitely presentedness is quite like that's restriction is like there is more restriction on that thing, so there does not exist much such thing. So finitely presentation is kind of a good notion. So one can ask also like for which spaces X this X is finitely generated but not finitely presented. A similar question one can ask even once we get X, whether that's true for only finite CW complex, or do we, if someone gets like an infinite CW complex, then whether that's true for some finite one or not. Those kind of results or like study was already done for certain other spaces. For example, like we have seen that this, if we consider Eilenberg-MacLean spaces, this KGN, the if X is there, then this is isomorphic to the automorphism group of G, right? So for these things, many people have studied like for which uh, X these groups, any if I pick any group G, whether those things can be realized as a uh, homotopy self-homotopy equivalence of some spaces or not, or when this space, this EX is trivial, when this is trivial for non, like definitely non-trivial, it's like non-contractible. This is one, and also, um, yeah, this is one another one interesting thing, and the other thing that was on saying that given a group G, um, whether G can be realized as some homotopy equivalence group. G can be realized as some EX for some space. Like as here, like for Eilenberg-MacLean space, it's like this is whenever we have a abelian group, then we can realize that as a space having that as a homotopy groups. So similarly, for any group and group G, whether we can whether that can be realizable or not. Definitely, those things have certain restriction, but in general, what we can say, whether it's realizable, which kind of groups are realizable as homotopy equivalences. These also I'm quite interested in, like for certain group, if there is some condition or not. But yeah, but I don't have much knowledge of how to attack those things. Uh, but these things seems quite interesting to me. And also there is also like for H equivalences also for rank one rank one H spaces, there is kind of almost like not almost for rank one H spaces there is complete calculation of this thing. This X, this epsilon HX, it's done. It's known. So, but for the so what about rank two? Rank two H spaces, what like what is this? So for certain space like SP2, that's a rank 2 space, SU3, those are calculated, but not all the rank 2 H spaces. So, um, uh, what about those things? Because already for those things also almost many classification is already done. Like what are all rank-wise spaces of X. So for other rank-wise spaces, just what would be this group? And there are also many other similar like such computation thing, not for all specificities known to this EX group is known. So whichever is not calculated, that's a problem problem to calculate. Uh, Also uh, to like okay, this is another one you already have told here like if X is simply connected, then we have a inclusion of these three things. So can we extend this as like extend on the left to get completely what are exactly complete relation between this EX, F, and EX if it is not in case like pi on X does not act trivially on pi n of X, pi n X non-trivially. In such cases, what is the exactly relation? What's the exactly relation? So that's another kind of mm, kind of way, like because the free thing is more uh, it has more application than the based one. So if we have some relation for those kind of the other cases as well, then it will help us saying just calculating the EX. We can say something about the free EXF as well. So these are few directions that one can pursue. So uh, I'll like I'm also still studying about those things. So if anyone have any query or any suggestion or like want to know or know something that want me to know, then I'm happy to answer those or like having further some collaboration if possible. Okay, so that's from my side. So I'll stop here. So if there is any question,
Okay. So yeah, thank you. Um, yes. So yeah, we don't have any
uh,
questions, so
okay,
uh, we can stop for now.
sure, sure.
So I'll announce for the next talk. Okay, bye for that time.